And we have Poisson distribution. I think it's attributed to a French mathematician, as far as I remember. I'm sorry if I remember it wrong. It focuses on a random occurrence of events on a given area or given time span. This type of experiments we're talking about here. For example, the number of incoming calls to a central in a given time span. The number of meteors hit in a specific area, the number of cells in a specific part of a tissue, or the number of radioactive particles emitted from a material in a given time span, or something like this. We're talking about those type of events. When your n grows, this is, I think, a very nice sentence. When your n grows in a binomial distribution, so when your n grows, your trials grow in a binomial distribution, Poisson will be its equivalent when your n trials goes to infinity. You assume like this, or you calculate it like this, which is very convenient to calculate. Let me try to show this to you on the board, hopefully. Gather. So suppose that this example is taken from your textbook again. Suppose that you're trying to calculate the traffic accident probability at a given location. I'm sorry, this probability is fixed. You're trying to calculate the, let's say, different combinations of this one, occurrences of this traffic accidents. This is your probability, okay? Having a traffic accident between, for example, those time span between 4 p.m. and 6 p.m., for example, and 10,000 cars pass by here within that time span. Okay, pass by. Now the question is, what we're curious about is what is the probability of having 2 or more accidents here? 2 or more accidents. You see your trials are 1,000 here. More accidents is what we're curious about. So your probability of x equals x is n. So you either have an accident or not, right? It looks like a binomial trial, so we calculate it like this. No problem. Oops. Q n minus x. And your probability of x equals x would be, now it will become a bit crazy. Just take a look at this. Over x times 001 over 10 and 999. Okay, it's complement over. What I'm doing is mathematically correct. It's wonderful, so no problem. But the thing is, probability of x equal to this one is what? That should be from x equal to 10, probability of x, calculate probability of x equals x here. But as you see, this is crazy, right? We cannot do this. The most convenient one is to calculate it like this. I think you are with me now, because this is much more efficient, as you see. And the result will be 1 minus, 10999 over 10. This is the probability for no accidents plus 1,000 times 0.0001 times 0.99999. Okay, this one. Okay, this corresponds to this one, hopefully, and this corresponds to this one. Now, even if you have a calculator, this is crazy, right? So that's where Poisson takes stage. Since it is hard to calculate, instead we use Poisson. Instead we use lambda, which is your NP, namely your expected value at L, when your n goes to infinity, like its limit. Okay, you can write this, or you can calculate this probability like this using Poisson. This one is over x factorial here, where your x can be 0, 1, 2, 3, blah, blah. It goes like this to infinity. And when where your E number is 2 point, it goes like this. It is also in your calculations. You can also use the table in your textbook for calculation as well. I think it should be, where is that table? There should be a table for this, for E, but I don't know whether. Oh, okay. We have a table, you see, for calculating e to the power minus alpha values here. It's a very convenient table that you have in your textbooks as well. This is what the author is talking about. And now in this sense, you calculate if we return to our question, our lambda is NP, which is 1,000 cars are passing by, and the probability of each of them having an accident independent from each other would be 0.0001, and the result would be, you are expecting, in fact, 0.1 accidents at any given time. So it is also your expected value, and it is also your variance lambda for Poisson. We're not going in detail for proof, but that's the idea. But you can see that it helps us to calculate now this one pretty easily. Now take a look at this. Of x equals 0 minus probability of x equals 1. Now you will see that it is much more convenient. E to the power minus 0.1, because we already calculated our lambda here. See? And times 0.1 over 0 over 0 factorial plus, not plus, I'm sorry, it is minus, right? So it is minus E minus 0.1, 0.1, 1 factorial. So the result will be 1 minus e to the power minus 1, which is 1 plus 0.1. This is its coefficient, and the result will be 0.047. That's the idea, and it's approximately, what is this? It's 0.47% or something like this. Yes, this is this is the probability that we're expecting for 2 or more accidents at that given particular time period. Now let's continue with another example to make this concept a bit more clear, hopefully. The other example given in the textbook is the number of particles emitted per minute from a radioactive material, which is lambda is 4 here. The number of particles per minute emitted from a radioactive material is 4. And in a randomly picked minute, any minute, what is the probability that, in a randomly picked minute, what is the probability that no particles emitted? The first part of the question is asking us this one. The probability of no particles emitted. Since its expected value is 4. Okay, what is this? So you can easily estimate that before solving it. It would be a low probability, right? Let's see. So, but anyway, let's calculate. It should be e to the power minus lambda to the power x factorial. This is the formula for Poisson. You need to memorize, I think. I cannot suggest anything else. The probability of x equals 0 would be e to the power minus 4 times 4 to the power 0 factorial, which would be this one. So it's approximately 1.8% probability that no particles would be emitted in a particular minute. And the second part of the question is asking, at most, one particle emitted at a given minute. At most, one particle. What does it mean, at most? Probability of, just understand the question very well first. Less than or equal to 1. So what you're curious about would be x equals 0 plus probability of x equals 1. That's what you're trying to calculate. E power 4, 0. Let me just put this here. Over 0 factorial. And your e to the power minus 4, 4 over 1, 1. Oops, it's not good. 1 factorial here. So the result will be 0.83. We have already calculated this here, right? So we're lucky. But anyway, you will have your calculators with you. So the result would be 0.96. So this would be your answer. It's approximately, what is it? 0.9% probability, I guess. Okay. And finally, the last part of the question is no particle emitted for 2 minutes. Okay. No particle for 2 minutes. Now be careful. Now your alpha becomes what? Pause the video and think about it. If you have 4 particles emitted as average, or this is expected for any given minute, for 2 minutes it will increase to 8, right? So your alpha will become 4 times 2, which would be 8 now. And what you're curious about is probability of x equals 0. In this condition, be careful. Now your lambda becomes 8 times 8 to the power 0, 0 factorial, and it is really a low probability this time, right? It's even less than this. You can also calculate this one with original alpha as well, original lambda as well, which is 4. Probability of x equals 0 times probability of x equals 0 will give you the same result with this one. Don't worry. You either do it like this or change your lambda, or change your lambda and do it like this. They will both give you the same result, and this is about the of Poisson distribution or Poisson approach to solving problems. And maybe you have already noticed that when can we go ahead and use directly binomial calculation here, or when can we switch to Poisson here? There is a rule of thumb here. If your trials are more than 20 and the probability of occurrence of what you're looking for is less than 5%, so it is a good idea to use Poisson rather than binomial. Or either this one, or if your trials are more than 100 and your n times p is less than 10 again it would be let's say convenient to use Poisson over binomial. These are some threshold values that you can make, you can take a decision. But in our cases, for example, about the traffic accident case here, it was pretty obvious, right? You had like 1,000 trials, and your probability of accident was 0.0001 or something like this. So it's pretty obvious that you need to use Poisson. So I hope that you have an idea about the discrete binomial. I hope that you have an idea about the discrete distributions up to now.